All right, good morning, everyone. I understand there's a question. Happy Father's Day. Thank you very much. I don't know if you heard my little speech. I'm dressed a little inappropriately in honor of it being Father's Day. I get to do what I want today. All right, so let's get started. I know last week's lecture was a little heavy. This one's going to be a little lighter. Oh, and by the way, to all my audience in India, I don't know if you saw, to what extent you care about Father's Day or not, but good luck against Pakistan. I understand today's the big match. All right, let me just get this out of the way. So first we're going to do, I want to, show you how to do some stuff with graphing in R so we can use it going forward. And then we're going to talk about correlation and causality. I mean, per se, just the statistics of correlation is not particularly hard, but why is that so big? Anyway, but there's some interesting things we're talking about. So you may recall that I gave you a rather crappy plot of a normal distribution, and I want to show you how to do a nice one. I'm going to use Ggplot rather than ordinary plotting, but I'm going to create two normal distributions. Remember, D is the density function, so D norm gives the density function, and so I just have x as my my x coordinates. So I'm going to go from a z-score of -4 to a z-score of +4 by 0.1. So I'm going to have data point every 0.1 between -4 and 4, and D norm 0, 2.5. That means the mean is 0 and the standard deviation is 2.5. And the other one is another normal distribution, D norm, the density of x. So it's going to give you the density, the values of the normal function at all values between -4 and 4 with value 0.1 for one whose mean is 0 and standard deviation is 1. I'm going to make this into a data frame simply because that's what Ggplot wants. Ggplot is always going to want a data frame. So I tell Ggplot, the first thing I do is I call the function and say that's my data, and this plus means, and now I'm going to tell it what to do. Geom line doesn't mean it's a straight line, it means you're plotting something. And this is much easier than in basic R. And the basic structure is always you tell it, you give it a mapping, which is, and I don't know why you have to have mapping equal, but they do. And the aesthetics is where you tell it the fundamental thing is aesthetics tells it what is the x and y. So here I'm giving x equals x, y equals y flat, and here I'm giving x equals x, y equals y peak, and I'm giving them different colors. And with Ggplot, when you do this, it's going to just keep plotting on the same graph. And then I just give it labels. You can look at it, and there we have. So there you have two nice things. And notice it's labeled, and I have the y value, and I have the z-score. So there you go. And for the same money, oops, excuse me, I can do the same thing with a chi-square plot. So the only difference is I make a data frame, and I use, instead of D norm, D chi-square. That gives me the density of the chi-squared, and here's a plot. So again, just as I said, the chi-squared values are calculated as the area under a curve. And you can see, though, with chi-squared, as the value gets larger, as your value you calculate gets further away from the value you expect, the probability of this happening gets smaller and smaller. Okay, so Ggplot is worth knowing. Why? It's easy to overlay, easy to create complex graphs. It has a consistent syntax, and it also makes it easy to analyze factors or categorical variables. Now, what I mean by that is sometimes you might have some data in a categorical variable, and with Ggplot, if you want to graph just all the different categorical variables and see how they differ, you can do that very easily. I will show you that in a second. Right, so here's something important. If you're interested in getting a cheat sheet which shows you the commands, you can just go to that or just Google Ggplot cheat sheet. This material mostly comes out of R for data science. Chi-square generally. Okay, let me answer that question in a second. I was asked a question about chi-square tests. So what I suggest, if people still have questions about chi-squared, let's take a few minutes to talk about it briefly after we finish talking about Ggplot, and then we'll move on to correlation. Okay, so the basic structure is you tell Ggplot what your data is, and then you tell it what to do. And there's all sorts of things you can do. You can do bar plots, histograms, points, lines. You can do smooth, which gives you sort of a confidence interval for the plot too. And as I said, the main thing is you have to tell it what to graph. Mapping equals, oops, that's an error, but it should be aesthetics. And you can pass other things, including colors. And so here I've just created a point plot, a scatter plot. This is a data set called MPG, which is about the miles per gallon of different classes of cars. And you can see here I said color equals class. There's different classes of car, and you see them on the side. And what Ggplot has done very nicely and very simply is it's colored every class with a different color. So looking at this, you can see as the displacement, the size of the engine gets bigger, the miles per gallon goes down, except for this group over here. So this tells you these are all SUVs. So it tells you SUVs don't fit in the pattern. And I would assume the reason is because while SUVs have a large engine, maybe they're not, built for speed quite the same way, an 8-cylinder engine car might be, so they get a little bit better gas mileage. It's the kind of thing you can see very easily. And here's another chart. I just did the same thing as a line chart. And here you can see, again, you can see that the SUV, sort of what's going on, is very different from all the other ones. And if you want a bar chart, use geom bar. And here I've given color equals class, and it shows you, so here it's giving you a count of how many cars are in different highway classes. And we can see that in general, things are like that. But this is a little hard to read. So instead of that, there's something called fill. So if you do fill, rather than showing you an outline, it actually fills the graph with the different pieces. And this gives you, here you can see, for example, now it becomes very clear that compact cars tend to have better mileage, and what's this blue? Oh my goodness, it's pickups. Pickups sort of be in a group with lower mileage. SUVs also, but the best ones are these compacts in terms of numbers. Okay, so if you read the text for chapter 10, it gave this Ironman Hawaii data set, and he was very happy with his plot, which shows you sort of how the swim speeds and the bike speeds compare to each other. So this plot is sort of saying, excuse me a second, I need to mute everyone. I forgot to. Sorry. That's not it. All right. Let's see, where is it? I always get confused. This is exactly where on the screen. I can do this. Sorry, I should have done this before. What was here? All right. I'm having trouble this morning finding the button that says turn off your mics. Maybe it's over here. Oh yeah, here it is. Mute all. All right. Okay, let me go back to the chat. Somebody has some questions. All right, so let me just finish up here with chi-squared. And with Ggplot, you can do the same thing, and that's very similar to the what the IMH what he did. But one nice thing with Ggplot is this data set is, and it does show that what does this data set show? People who are poor in swimming are poor in biking generally, and people who are good in one tend to be good in the other, but there's quite a bit of variance. But for example, one of the data points is gender. So I can also with Ggplot, just by saying color equals IMH $gender. And remember, IMH $gender is just the gender, which is male or female. I can now get a nice plot which shows you how men and women are separate, you know, how they separate along this. And it's kind of interesting. It just shows you there isn't much difference. Probably what this means is, except for the really best people, who are a few people who are sort of way out here, there isn't much difference between men and women. And the other thing is facets. What facets do is they create separate charts based on a categorical variable. So in this case, I have the categorical variable gender, right? And I created a chart, a point, you know, a scatter plot with the genders, male and female, that's separated by color. If I do facet, it'll create separate charts. So here's a chart for the females, and here's a chart for the males. Okay, so it allows you to do that, and this is very good for analyzing data. Now, the other thing you can do with Ggplot, well, you can do lots of wonderful things with Ggplot, and you know, if you start poking around, you'll find lots of packages. One of the nice things about Ggplot is it allows it for the creation of extensions, which are packages that rely on Ggplot, keep the same basic structure of Ggplot, but do additional things. So this package Ggalley allows you to make very nice correlation plots. And as I said, you can read more information there, and if you want to do these things, you should. So we have this data, and I'll discuss it more later, but here's a correlation plot of it. And you see it creates a heat map of the correlation of the different variables with each other. Of course, so -1, it says V4 is not very well correlated. It's negatively correlated with the others. Y5 is pretty highly correlated with everything in a positive way except V4. So you can do things like that. And here's just another example with another data set. It shows you, it allows you to see very nicely, well, depth and table are the two that are negatively correlated. All right. So before I get started with correlation, I was asked a question about chi-squared, and I want to answer that. It says, how do you determine which statistical test one should do is the thing? Because, you know, people, as everyone's familiar with, you know, normal distributions and doing a test, does it fit into a confidence interval? The answer to that question, depending upon how you want to think about it, is incredibly impossibly hard, or rather simple. And let me take the simple approach, which is most of the time the data suggests what you want to do. So if your data is roughly normally distributed, computing a t-score or a z-score and seeing what it is going to be the good statistical test. Now, a lot of times data is not just normally distributed, and if you go back to the previous lectures, I talk about bootstrapping. Now, bootstrapping is a method for sort of creating confidence intervals that doesn't involve any hypothesis of normality. Sometimes people use the word non-parametric. So that's an important tool to have in your practical one. Now, the chi-squared test, you can, if you're just sort of saying, when do I use a chi-squared test as opposed to, say, normal distribution, that's pretty easy. The chi-squared test is for counts. Now, counts, you don't have, far from having, you know, continuous data or anything that looks like continuous, counts you only have integer values. So you might recall that for the cigarette data, you had counts of how many people with cancer and without cancer were in the groups, different smoking groups, from 4 or less cigarettes up to 50 or more a day. And you had these 2 different counts, and you wanted to see whether, there was a difference. Okay? Let me just go back here a little bit. So, okay, let me go to my R screen. So, summary, sorry. So this IMH data set, it has a variable gender, category, which we can ignore, and then swim, bike, run. So one thing you might say are the men as good as women? So you would have men and women, and you'd have swim, bike, and run. Now, if you look at this as continuous data, you could, this is going to be complicated. But we see here we have the minimum, the first quartile, the median, the third quartile, and the max. Okay? We could separate these out by men. So we could, see how many men were in the bottom quartile, how many women were in the bottom quartile, how many men were in the second quartile, how many women were in the second quartile. And you could compare whether men and women swim as well as each other by that way, by comparing the counts. If men and women were equally good at swimming, you'd expect there to be about the same number of men and women in each category, and the chi-squared test will allow you to do that. The quintessential example of something like this is you flip a coin and you want to know if it's fair. You know if it's fair, you expect 50 heads and 50 tails. But as the first example, if you flip it 100 times and get 80 heads and 80 tails and 20 tails, is that good evidence? So chi-squared is used when you have counts, right? Are there any other questions about chi-squared or about Ggplot? All right, so I've given you a brief introduction to Ggplot now twice, and going forward, I'm going to use it. If you have questions about the syntax when I actually go and use it, please stop me then. But hopefully the 2 introductions have gotten you familiar, and I can't say enough good things about Ggplot. It really, if you just want to see a scatter plot, plot x comma y will work just fine. But if you want to do anything fancy, if you want to make nice graphics, Ggplot is really fantastic. Doing things like these heat maps is just wonderful. Okay, so on to correlation. So I call this smoke, fire, cause, and correlation. And the reason for that is, of course, there's 2 famous adages in statistics: where there is smoke, there is fire, and don't confuse cause with correlation. So the goal of this lecture is to explain why I don't think there's a contradiction between these 2 statements. One seems to say that if, the obvious thing occurs, the conclusion, and the other one says, well, just because you see smoke, we know smoke is correlated with fire. We don't know that there's actual fire. So hopefully this lecture is going to clarify that. And if I just wanted to talk about the mathematics of correlation, this would be a very, very short quiz. But I really want to put this in the context. I want to sort of give you guys some understanding of how you have to think about these things when you find correlation, when you don't find correlation. And so that's what we're going to talk about. Okay, so the goals for today is talk about the difference between cause and correlation, explain that they really are different, talk a little bit about the geometry, which is how you can think about it, mention different measures of correlation, and show how it can be used to understand data sets. Of course, number 5 is the goal, using it to understand data sets. But understanding the difference between cause and correlation is a big deal. Okay. So what is correlation? I will write down mathematical formulas or show you mathematical formulas later, but for right now, suppose we have n measurements of one data set, x, and n measurements of another data set, y, and we have some way to connect them. For right now, we'll just say that x and y are correlated means that they vary in the same way. In other words, when the x data changes in a certain direction, the y data changes to do it in the same way. So A classic example of correlation is Salk and Sabin are two vaccines for polio. Jonas Salk and I forget Sabin's first name, both came up with vaccines. And prior to the vaccine, people noticed there was a strong correlation between ice cream sales and polio. And what that means is that when ice cream sales went up with an appropriate lag, so did the number of polio cases. And when ice cream sales went down, so did polio cases. So let's see, here's quiz one, and hopefully this week they're going to show up. Let's see. No, they're not showing up. All right, so you're going to answer this with the quiz, please. I'm going to have to figure out this problem. They are definitely posted there. So the quiz is, you have this connection between ice cream and polio. And from this, what can you conclude? And my four choices are: ice cream causes polio. In other words, because you see this connection, whenever ice cream sales goes up, so does polio. 2, polio causes people to eat ice cream. 3, polio comes from ice cream. This would show that whatever's causing polio, it's in ice cream. And 4, if something connects polio to ice cream eating, even though ice cream and polio aren't connected. And currently we have, let's see what answers we have. I saw one answer for 4. All right, so give this a thought, please reply. Ice cream causes polio. Polio causes ice cream. Polio is somehow in ice cream. I mean, food poisoning can be connected with ice cream eating. All right. So everyone who's answered says 4, and that's in fact the right answer. Something connects polio to ice cream eating, even though ice cream and polio aren't connected. And the answer is, what connects polio to ice cream is summertime. When it's summertime, people eat ice cream. But when it's summertime, kids go outside and play with each other a lot. And polio is infectious. So it spreads best in the summertime when there are more people to infect. So good weather is actually the causal connection between polio and ice cream. Polio and ice cream are correlated. Good weather is the cause, because when you have good weather, people see each other more. As I say, sometimes this is called a confounding factor. So this is worth noting. Incidentally, another very good example of this is the influenza epidemic of 1919. There was a worldwide, there was a pandemic in 1919 with the flu. And what happened was that in the winter of 1918, people thought it went away, and in 1919, people started, celebrating again, and it came back with a vengeance. And of course, what had happened was they had a very bad winter in 1918, so people stayed indoors a lot and didn't connect to each other, so it didn't spread a lot in the winter. But as soon as the weather got nice in 1919, it came again. So, in fact, ice cream is a confounding factor. Now, if you're interested in prediction, a correlative relationship may be enough. So in other words, if you're trying to model when is there going to be an increase in polio, you could look at ice cream sales. Now, it may be enough, but it's rarely going to be optimal, because if two variables are correlated, that means they're reasonably well connected, but the connection is typically going to be far from perfect. So in other words, if you can find the real causal variable, you can build a much better model. Now, if you're interested in cause, in other words, if you want to say, ice cream causes polio, therefore we should ban ice cream, then a correlative relationship is never going to be enough. Until you can show that ice cream causes polio, and it doesn't, you can't do it. And let me just make an aside on that. Last week in the Chi-squared, we looked at the cancer data. And the point of that was that showed that there was a link between cancer and smoking. Doctors had suspected it, but with that study, they were then able to go out and do research and discover that, in fact, there was no there was, in fact, a causal link that if you smoked, it did increase your chance of getting cancer. But that study didn't show it. It just showed they were correlated. So if you were going to use the study to predict who was more likely to get cancer, it was fine. But if you're interested in saying we need to tax cigarettes, or we need to ban cigarettes, or we need to warn people about cigarettes because cigarettes causes cancer, that study wasn't enough. And to find cause, one has to do a controlled study. And what does that mean? Well, let me just say that it says if cases are randomly picked and you find correlation, it's more likely to be causal because you weren't just given the data. So in the case of ice cream and polio, it's a simple example, but that's not a controlled study. In a controlled study, you would randomly pick 100 people, 50 of whom ate ice cream, 50 of whom didn't eat ice cream, and you would see if their polio rates differed from one another. So you see these kind of controlled studies a lot in medicine. You don't see them a lot in the real world because most of the cases, you can't do a controlled study. You just have to try and figure out what's going on. I mean, if you're doing marketing research, people aren't going to do controlled studies. You can't randomly divide people into two groups. The data is what you have, and you have to see what you can find in it. So controlled studies can change a correlative effect to a causal effect, but it's typically in the real world. In most businesses, it's hard to do them, except in medicine, where people have paid lots of money to do them. Now, we're not going to discuss this at all, but I just want to say it's not hopeless. There are things called A/B studies. They're not quite random studies, but they're very useful, and they're used significantly in marketing. Or, for example, at a company I used to work for, when they wanted to have a new feature, they wanted to see if people liked them or improved it. So they do A/B studies, and what they would do is they would turn the feature on for a certain number of cities and turn it off for other numbers of cities, and see if they could notice any difference in effect. These are not quite random because you have to do it for everyone in a city, but they're close. Okay, I want to do one more example of causal behavior because it'll be a nice warm-up. It goes back to chi-squared, and also because it's a wonderful example of how you have to be careful with what things mean. And this frequently goes under the name of Simpsons Paradox, and it's so famous that the data set of Simpsons Paradox is already in base R. It's called UCB admissions, and I'm just going to change it to being called UCB because UCB is easier to type than UCB admissions. And so I create this object UCB. In R, pretty much everything's an object, and I say, what is it? It's a table. So a table is just what you think it is. It tabulates. But when I go to summary UCB, it says number of factors 3, so it's a three-dimensional table, and those get a little tricky to understand the third dimension. So let me just skip ahead for a second. Let's see. But if you, maybe over here. Summary UCB. Okay, that's the wrong one. You see there's 3 factors. So as I was saying, excuse me, let me get back to the, oops. Yeah, so a table, normally you think it was 2 by 2, but by saying it has 3 factors, you're really saying that there's a bunch of tables. Okay, so what does it say? Number of factors is 3, test for independent. So here it does. It gives you a chi-squared test, and it gives you a p-value of 0. So let's analyze what this means. You might want to, if you looked at the structure, you would see the third factor is the department, and there's 6 of them, A, B, C, D, E, F. And you might go to say, well, let's look at over the sum over all the departments of the table and see what we get. This is not what we want. But when you run into this problem, there's a simple solution. Tables look like matrices. They're counts, but they're counts in the form of a matrix, so they can be added. So I create a matrix matrix 0, 2, 2. This means a matrix with all of whose entries are 0, 2 rows, 2 columns. So that's a table. Okay, now for I equal 1 to 6, I add to UCB all my table from UCB, all the variables but for the ith department. So this is a three-dimensional table, so you have 2 commas to say I want all the values for the first variable, all the values for the second variable, and then add it over this thing. And when you do this, this is what you'll get. You'll see that it's male and female, admitted, rejected. So what I've gotten here is I've created a table of men and women and whether they were accepted or rejected by UC Berkeley. The individual tables look like that by department. So for example, if I do UCB, comma, comma, 1, I just get for Department A, the acceptance and rejectance. So for Department A, we have this table. In the men, 512 were admitted, 313 were rejected. For the women, 89 were admitted, 19 were rejected. Now, as a hint, I just point out to you there's way more men than there are women in this. Okay, so here's the data. And what happened was some people looked at this data and said, well, women are getting rejected far more often than men. Okay, and we can see this better if we use this other command, prop.table, that stands for proportion table. And proportion table will just create a table where instead of giving you the raw numbers like this, it gives you the percentages. So guess what? You add up these 4 numbers and you're going to get about 100. 58, 60, 70, yeah, so you get about 100. So you can see 26% of the men, 26% of the people were men who were admitted, 32% men rejected, 12% female admitted, and 28% female rejected. And you say, hey, this makes it abundantly clear that way more women are getting rejected than men. And UC Berkeley was sued on this basis. And here's where don't abuse causal correlation becomes in. So looking at table 2, we can see that 45% of the men and 30% of the women are admitted. Okay? So I'm just telling you that 26% is about 45% of 26 plus of the 58, 59% of the population is men. And on the other hand, 0.12 plus 0.28 is 40, and 12% is 30%. So in other words, the ratio is clearly different. 45% of the men and 30% of the women are admitted. Okay, and my question is, does this data prove there is discrimination? Or 2, does this data provide evidence of discrimination? Or 3, does the data doesn't provide evidence of discrimination? I mean, if you look at it, you say, well, 45%, 30%, that isn't that big a difference. That would be answer 3. Answer 1 would be, I'm suing you because you are rejecting women far more often than men, and this proves that you discriminate against women. Or does it say, well, maybe this looks like discrimination, we need to look at it. So those are your 3 choices. I await your answers. All right. The data doesn't provide evidence of discrimination is the only one we have. Okay, so maybe 45 and 30% admission rates are close enough together. Anyone else want to take a guess? There is no penalty. Okay, so what's the answer? Get this out of my way. Well, the first thing is I like this cartoon, which is pretty much a standard cartoon on this thing. Yes, on the surface it appears to be sex bias, but let us answer the following questions. Let us ask the following questions. So the data doesn't prove there is discrimination. It seems to show that there's a connection between being a man and getting admitted. Okay, So the data provides evidence of discrimination. Perhaps the better answer would have been the data provides some evidence of discrimination, as the picture shows. Okay, so as I said, the data shows there's a correlation between being a man and being admitted. Now let's getting back to the question I was asked. How would you test this? This is count data. We have counts: number of men and number of women, admitted, not admitted. It's a 2x2 table, in fact. Here's my 2x2 table, and they're counts: men, women, admitted, rejected. So chi-squared testing works, but remember, if you have a 2x2 table, there's something called the Fisher exact test, which not only will answer that, but will give you more information. And we do it, the Fisher dot test UCB all. And it's basically saying what's the probability that the men and the women admission odds are the same given the data you observe. And so the probability of this happening is extremely small, less than 2.2 to the minus 16, that's the smallest number R has. So remember, R is a computer. It doesn't have actually infinitely numbered numbers. There is a smallest number. So this would mean you would definitely accept the alternative hypothesis that the true odds ratio between men acceptance and women's acceptance is not 1. And then it gives you more information. It says 95% of the time, if you observe this data, the true ratio between the men's acceptance rate and the women's acceptance rate is 1.62 to 2.0. And in fact, you would calculate that it's 1.8 is the ratio. So this does look like there's sex discrimination, but, and to continue on the next slide, it's a really big but. And like sanctimoniously, rather than just accepting guilt, UC Berkeley said, we're liberals, we don't discriminate, this couldn't possibly be true, and they hired some statisticians to fight this, and they won. The statisticians went to court and said, this does not prove this discrimination. And why? And the reason why is, remember, you really had not just a table of men and women admitted, but you had 6 departments with different admissions. So, all this does, remember this is a for next loop, and R is just, you just say for I, and it's always good to put the numbers you want it to run from in parentheses. Sometimes it's not going to change things, but particularly like, for example, when your indices are a functional thing, instead of from 1 to 6, it's 1 to 2 times some variable plus 3. If you don't put it in parentheses, you're not going to get the right looping action. So for I equal 1 to 6, over each department, I want to print, which means print to the screen, the proportion table. Okay, so round means I just want it to 2 decimal places. That's why you're getting 0.55, 0.34 rather than things, and round 2. Proportion table gives me the percentage, and the UCB data, comma, comma, I means the table for the ith department. And here it is. And I claim that if you look, well, here, this department looks worse, but it's small. This looks less clear that there's discrimination, and in fact, let me explain what the code does in a second, but if you look per department at the acceptance rates, right, you see for Department 1, significantly more women, Department 2, a few more women, Department 3, a few less women, Department 4, a few more women, Department 5, a few more men, Department 6, about the same. So while overall men are being accepted in greater numbers, if you look at every department, there's no department in which you can see this huge discrimination. Right? Now, let me see, do I have a quiz? Right, so let me just explain how I got this data. I created a matrix. So I want to create this matrix that's going to show me department by department the male acceptance rate and the female acceptance rate. So I create a matrix with 6 rows and 2 columns, 1, 2, 3, 4, 5, 6 rows, 2 columns, and I give the column names, male acceptance, female acceptance. And so what I'm going to do is I'm going to again loop over all the departments, UCB I, comma, comma, I, all right? This means I look at the ith table. 1, 1 is the number of men who are accepted. 1, 1 and 2, 1 that's men accepted, men rejected. So this is going to give the ratio of men who are accepted. And then similarly, 1, 2 is the women who are accepted, women rejected. So the second piece gives me the percentage of women who are accepted. And then I'm just saying C means combine, so that means make it 2 numbers. So that means you put these 2 numbers over there. And then I printed it out. So here we have it. When you put all the data together, this seems to be evidence of discrimination. But again, let's look at chi-squared. Now why am I doing chi-squared? Because now I don't have a 2 by 2 table. So I have a 6 by 2 table. 6 rows, 2 columns, right? So I can't use, or I shouldn't use Fisher's test. I should use chi-squared, and I can do chi-squared dot test of yin-yang. And what's that 5? Okay, impromptu quiz. Who remembers what the 5 means? All right. Anyone? Okay, I'll give you a hint. It's actually on this page, if you look. All right, 5 is the degree of freedom. Remember, for a chi-squared test, you need to, the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. 6 minus 1 is 5, 2 minus 1 is 1, 5 times 1 is 5. And the point is the degrees of freedom, as you have more and more degrees of freedom, you get different amounts of information. It becomes, you know, if you have much larger degrees of freedom, you could expect much larger variances to have to still mean things are okay, because there's a lot more ways where things can vary from what you exactly expect. Now, when we do the chi-squared test for this data, yin-yang, and this is the data of male versus female acceptance rate by department, it says we get this small chi-square value, df equals 5. That's why I said that you could get the answer from here. So you have 5 degrees of freedom. I put them in. It says p-value 1. What's the hypothesis? The hypothesis is that these ratios that you're seeing are drawn from the same pool. So the hypothesis is the male acceptance rate is the same as the female acceptance rate when you look across all departments. So here it's saying the p-value is 1 means you with almost moral certainty, you accept the hypothesis that there is no difference between the men and the women's acceptance rate. And this is what the Berkeley statisticians went to court and argued, and they won. Okay, so I pretty much explained this to you, but let me give you quiz 3, which says when you look at this chi-squared table and this information, p-value equals 1, degrees of freedom is 5, and this chi-square value that's very teeny. This tells you that with probability essentially 1, the male acceptance and female acceptance rates are the same. No, I see this is a problem here. I have 2 2's. Well, let's leave out the second 2. 2, yin-yang is a bad name for a variable. And 3, we need to do a Fisher exact test to find out the answer. So your 3 choices, and I'm going to wait and give you some time. I do want to see what your answers are. It says with probability 1, the male acceptance and female acceptance rates are the same. Yin-yang is a bad name for a variable. And 3, we don't know. We need to do a Fisher exact test. Okay, we have 1, we need to do a Fisher's exact test. Oops. We have another one with probably 1. Okay. I'm just tabulating. We need to do a Fisher exact test as 3, and with probability 1, male and female acceptance rates are the same. Okay. The hypothesis of a chi-square test is that the two samples are drawn from the same distribution. So p equals 1 is very strong evidence of the null hypothesis that the two data sets come from the same distribution, and hence with probability essentially 1, male acceptance and female acceptance rates are the same. Okay, yin-yang is a bad name for variable, and that's, one can have an opinion. You can't do an Fisher's exact test in this case, or you shouldn't, because you have 5 degrees of freedom. You don't. If you just had 2 departments, you could do a Fisher's exact test. 2 by 2 tables are very special. Okay. So the correct answer for this is that probability 1, there is no evidence of discrimination in the data. And this is called Simpsons Paradox because it seems paradoxical that when you look at the data finally, you see that there's no discrimination, but when you aggregate the data, you get a very different answer. And this, by the way, so there's the moral of the story is that aggregating data can lead to wrong conclusions. So it's called a paradox. It's seemingly paradoxical. And what's the answer? And the answer is that women tended to apply to departments with very high rejection rates. So I'm off the top of my head, I want to say that men applied for departments in sciences which had very high acceptance rates, whereas more women and very rarely applied for departments in the social sciences like anthropology, sociology, and those departments had very high rejection rates. So more women were being rejected than men because they were applying for departments that had way higher rejection rates. Men were applying for physics and chemistry, and almost everyone who applied there got accepted. So that's incidentally the explanation for the paradox. Okay, so it's just about time to talk more seriously about the mathematics or the structure of correlation. But before I do so, are there any questions so far? Are you okay with Simpsons Paradox? Are you okay with this? You're getting a little more happy with using chi-squared for count data? All right. Right. Somebody made the point that you could also argue with this data on other points, that the study doesn't account for things like minimum test scores or grades and previous things, and this is true, and that's a nice piece of critical thinking. I mean, and this is something that you need to do when you have real world data, when you have a data set and you said, here, what does it mean? You have to understand what you're given. So I didn't write this example down, but there's another famous example in medicine where a large number of studies seem to indicate that a certain treatment was useful and a small number didn't. And then it turned out that the small number that didn't were the right ones because they were the ones that had done some critical thinking about different variables and had done better versions of double-blind testing. And the studies that showed that the treatment was successful did not attempt to account for various aspects of the data that was there. For example, that the treatment was typically given to people who weren't as sick, so of course they had a better survival rate. All right. Any other questions? All right, let's move on. So correlation is a way of measuring a connection between two data sets and how well they're related. And I want to stress this, how well they're related in a linear fashion, which is to say, when one goes up by a factor of something, the other one goes up in a similar amount. And it varies between +1 and -1. A correlation of +1 would mean that they have the perfect linear relationship. The two variables go up linearly. If you drew a graph of x versus y, if you plotted it, it would be a straight line. A correlation of -1 means a perfect negative relationship. So it's also a line, but it's a line with a downward slope. It means whenever x goes up by a certain amount, y goes down by some linear amount. A correlation of 0 means that there is no linear relationship. Now, correlation of x and y being 0 does not mean that there's no relationship between x and y, but just that there's no linear relationship. It may mean there's no relationship, but it doesn't prove it. And I'll give you an example of that in a second, but just for example, if y was the logarithm of x, there'd be a perfect relationship between x and y, but there would be no actual linear relationship. Okay, so here's the formula. Here's a complicated looking thing. The correlation of x and y is for the data set x, you subtract off the mean from each observation, and you multiply it by y minus its mean, right? So you look at xi minus x bar times yi minus y bar, you sum that all up, and then you divide by the standard deviation. Okay, so when you put this into formula, you have the same numerator, and then the denominator becomes this very, very large and messy thing. But that's the exact formula. Now, of course, you're never going to have to do that by hand. R will do that for you. Let me just skip ahead for a second. Just the command is core, C-O-R. But this is a very complicated and nasty formula, but it's really saying something pretty simple about the relationship in x and y, and I'd like to describe that to you with a little linear algebra. So just remember, so if you have a data point, a data set which has n values, and you have another one y, you can think of your data points as being points in an n-dimensional vector space. Okay? And with linear algebra, there's something called the dot product. If I have two vectors, I can take their dot product, and it's just you sum up the coordinates, which is kind of like this, except we have to subtract off the mean. And you don't do that here. And I'll explain why in a second. So this dot product really tells you something about the geometry. X dot x is the length of the vector. So in other words, if you have a vector, now over here it's called A and B, but if let's just say this is the vector A dot A would be the square of this distance from the origin to A. Okay? And there's a very famous mathematical fact called Cauchy-Schwarz, which says the dot product of x and y is the cosine of the angle between them times their actual lengths of those two vectors. So x and y is the product of the lengths of the vectors modified by the cosine of the angle. Now remember, the cosine of 0 degrees is 1, and the cosine of 90 degrees is 0. So what does that mean? It means if x and y have an angle of 90 degrees, their dot product is 0. There's no connection. They're different variables. And if x is a vector of length x, that length is the distance from the point of x to the vector 0. Okay? And so here's the diagram. Here's the origin. Here's the vector A. Here's the vector B. And this angle theta is what's given by the dot product. So in other words, x dot y is that angle theta times the length of x times the length of y. Now, what does this mean? And as I said, the cosine of 0 degrees is 1, and the cosine of 90 degrees is 0. If A and B were absolutely the same, the cosine of 0 means that one's just a proportion of the other. That's linear relationship. If the cosine is 90 degrees, they're uncorrected. I mean, it means they're just completely different variables. There's no linear connection. So the geometry is that you subtract off x bar and y bar because you get the length by having picked the distance from an origin, and the origin is x bar and y bar. So that's why when you want to understand the correlation, you first have to subtract off the means. Okay? And so the correlation between x and y is the cosine of the angle. So I don't know how many of you thought about it, but if you have 3 points, they always determine a plane. So in fact, if you have a chair with 3 legs, it's always going to be sturdy. It's never going to have one leg longer than the other. 3 legs will always exactly fit on the floor. They're not on a line, right? So if I have my 2 data points, x and y, and I take my 3rd point to the origin, which is why I subtract off x bar and y bar, you're always going to get a plane with the point x, the point y, and the origin, and then you can calculate this cosine theta. So the correlation is simply tells you whether one point, how close one point is to being just a multiple of the other point. That's what a linear relationship is. And so as I say, that's the linear relationship. The correlation of xy is the cosine of the angle between the 2 data points. Nonlinear relationships will not be found by correlation. The other thing I want to say is sometimes you have covariance. So covariance is on the scale. So the covariance of xy is just the dot product. It's just given by this formula. And it's typically less useful because it doesn't take into account the scale of x and y. So let's do some examples. So let's create a bunch of variables or data sets. I'm just going to have x is 1 through 100. And E is a matrix of noise. R norm means R normal, so that's 100 normal data points. Remember, if you don't specify, this means mean 0 and standard deviation 1. So this is 100 random values that are distributed with mean 0 and standard deviation 1. The first variable y1 is going to be 2 times x. Now here's a perfect linear relationship. Okay, so y1 should be perfectly correlated with x. y2, I'm just going to take the same thing and add a little noise. It should be essentially perfectly correlated. y3, I'm just taking the negative. So it should be essentially, you should get -1. y4 is cosine x. Okay, so this should not be a linear relationship. y5 is going to be x again. So the correlation of x with itself is the covariance. And y6 is going to be x to the 20th power. So let's take a look and see how these things correlate. I create a data set. Look, I see bind x with all of these variables. And then the round comma 3 means just giving me the answer to 3 decimal places. So I look at the correlation of this data set, and it does it. Now remember, correlation is between 2 data sets. It doesn't make any sense to talk about the correlation y1, y2, and y3. But what this does when you do correlation like this is it gives you a matrix of all the answers. So notice there's ones down the diagonal. That's the correlation of a variable with itself. Okay? So the correlation of y1 with y1 is always 1. The correlation of y6 with y6 is always 1. And incidentally, it's symmetric. The correlation of y5 with let's make it y4 with y1 is 0.012 is going to be the correlation of y4 with y1. So you really only need the entries either above or below the diagonal. But what this will do when you do correlation is it'll understand you mean that, and so it'll just give you the correlations of all the different variables with all the other variables in the form of a matrix. Okay? So that's how you do that. And incidentally, if you wanted covariance, now notice, what was it? Y5 is x, and notice the covariance is 1 because these were scaled. Notice, now look at y6 was x to the 20th power, so the correlation of x with y to the 6 is about 0.5. Now there's an exact relationship between y6 and x, but it's not linear, and that's why it's 0.5. And instead of taking 1 to 100, I'd taken 101 to 200, this correlation would go down significantly because, for small values, it's not that much different. Let's see if what I said is correct. So here's something I can do very quickly. I can look at the correlation. I think this will work, of 101 to 200 with 101 to 200 to the 20th. Let's see if this will work. I guess the bigger numbers actually make it better. But you see what I did here. All I did was I took the correlation. My first data set is numbers 101 to 200, and the next one is numbers 101 to 200 to the 20th power. It just very quickly spat it out for me. Okay, so that's how you do it. And all I did here was create the scatter plots of those 6 data points, and you can see very good linear relationship, almost perfect linear relationship, almost perfect and then negative. This is the one that had the -9. Here there's no relationship. Here this is the perfect relationship. And this is, you can see it looks linear for most of it, which is why you got the correlation 0.5, but somewhere around 80, it starts looking highly nonlinear in a different fashion, and that's why you didn't get a very good thing, a very good correlation, even though it's a perfect relationship. Okay, last quiz for today. I have 3 data sets, X, Y, and Z, and I know the correlation of X with Y is 0.1, and the correlation with X and Z is -0.8. So, which of these statements is true? X and Y are more closely correlated because X and Z have negative correlation. X and Z are more correlated because they have a larger coefficient in absolute range, and X and Y have no causal connection. In other words, there's no way to connect X with Y as a function of the correlation of X and Y being 0.1. So we have X and Y have no causal connection. Let me get this out and let's see what kind of answers we're getting. Okay, I have one answer for X and Y have no causal connection. Anyone else? We have one for X and Y are more correlated because X and Z have negative correlation, and we have one, another one for that. One for X and Z are more closely correlated. Another one for X and Z are more closely correlated. Okay, I'll give you another 30 seconds to think about it, and then we'll go on. All right, so what does this mean? The correlation of X and Y is 0.1 means there's essentially no linear connection, but there's no correlation between X and Y. That means there's no linear connection. As we saw over here, if we looked at the correlation of X with Y4, there's almost no linear connection. Y4 was the cosine of X. So X and Y having small correlation doesn't mean they're not connected, it just means there's no connection. Correlation of X and Z being -0.8 means that they are very closely connected. There's a strong linear relationship. It's just that when X goes up, Z goes down. When X goes down, Z goes up. So X and Y are more closely correlated because X and Z have negative correlation. I say that's not true. X and Z have large negative correlation, and per se, you don't care. You don't like Z? Make it -Z. X and -Z will have correlation 0.8 because -Z is going to go up by the same amount that Z goes down. So X and Z are more closely correlated because they have a larger coefficient. That is correct. X and Z, Y are more closely correlated because X and Z have negative correlation is not correct. X and Z are pretty well correlated. If you were looking for smoke and fire, you know, here's a strong connection. When X happens, Z tends to happen. It's just Z moves in the opposite direction. X and Y have no causal connection. We don't know. We just know they're not correlated. They could have very strong, they could be perfectly then. What if X and, my example was Y is cosine X? There would be an exact causal connection, but there would be no linear connection. All right, so X and Z are highly correlated. X and Y are small correlation, positive and negative doesn't important. Okay, so let's talk about the data set that was in the text. Chapter 10 you were asked to read, and it talked about the IMH data set, which is Ironman Hawaii. Now, if you wanted to play with that data set yourself, you'd say, well, how do I get it? I just Googled IMH212.txt, and it took me to this page right here. Let's go to that page right there. So I see this, and I see it's a data set, and there's a few things I can tell you off the bat. The first line is headers, the categories. Secondly, the data is the first three variables are, these are just the row numbers. The first two are categorical variables, gender and category. And then swim, bike, run, overall, these are times. So I'm going to have a header. And the other thing I notice is that they're separated by just space. So I can use read.csv. Read.csv, I just put in the web page. I tell it has a header equals true. Strings is factor equals false. That's something you always want to put in unless you want the strings to be factors. And then the separator is just space. So I can create this data set IMH, and it reads it in. When you use read.csv, it creates a data frame. And I get a summary. The first two are characters, so it doesn't say anything. And then for the swim, bike, run, and overall, it gives me the standard information, the min, the quartile. All right, so you want to say, what's more important to winning, swim, bike, or run? So I just want to look in that order. So I'm creating a new data set IMH2, and I'm just going to make it IMH of 6 and 3 through 5. 6 is the overall. I want that variable to be first, and 3 through 5 is swim, bike, and run. And then I just do the correlation. As I said, for neatness sake, I make it the round of the correlation to 2 places. So I'm just going to get 2 decimal places. And of course, overall is perfectly correlated with overall. Swim is perfectly correlated with swim, da-da-da. But what's overall most closely correlated? There's a 0.76 correlation between swim and overall, 0.93 for bike, and 0.94 for run. Now notice if swim and overall have a 0.94, we could also do it this way. I could go to the run column and look and see overall versus run is 0.94. So you only have to look at the top. So those are both very strongly. It seems like swim is less likely to be important. So let's see. Nope. Okay. So based on this, and this is quiz number because I didn't make it a quiz per se. I just want to talk this through. Well, if you want to make a guess, based on this chart, would you believe being strong in swimming is the key to winning? Being strong in running is the key to winning? Being strong in biking is the key to winning? Or being good at punching at the water was important to winning? So let's just talk through this. Well, swimming seems to be less likely. If you have 2 guys who are going for this and they're competing, and one's really good at swimming and the other's really good at biking, you think probably the biking guy is going to do better overall. That's what the data says. These are empirical studies, 0.93, 0.94. If one guy was good at biking and the other guy was good at running, I wouldn't particularly want to favor one or the other. But either good at biking or good at running, I take that over swimming. So believing good at swimming is the key to winning doesn't seem to be true. Believing good at being strong at running, that may be. And as I said, I would suspect either being strong in biking or running is about equally important. Think being good at punching in the water was important. Well, this data doesn't say that, but I actually have a friend who competed in the Ironman Hawaii and a few others. And he said people are incredibly dirty. And when they're in the water and when they're swimming, they'll pretend they're doing an overhand stroke, and they will just clobber you in the head and push you underwater. So he was actually a martial arts fighter, and so the fact he was really good at punching in the water was important. He wasn't a very good swimmer, but he didn't get pushed way behind because people who hit him were punished in rather painful ways, and people quickly realized that Pat was just not the guy you wanted to play your dirty tricks with. He knew a few they didn't know. So turns out that, and this is a perfect example. Here's some information that's just not in the data set. Actually being good at martial arts is very good. And just for the record, Pat, is not a professional. He was in no danger of winning. He was in danger of doing okay in his age group. He was very weak at swimming. He was much stronger at running and biking. Okay. Any more questions on the IMH data set? So that's just a little overview of some of the things they talked about in the text. All right, so in talking about correlation, this is called Pearson correlation. There are two other kinds called Spearman and Kendall. And if you use question mark core to see what's going on, you'll see that you have X and Y, and Y equals null. This is saying if X is a data matrix, you don't need to put in a Y value, use everything. And then method, Pearson, Kendall, and Spearman. So Kendall and Spearman data sets are important for, they're less important, but they're important. They're ways of sort of connecting ranked data. So if you have ranked data, you would use these. And I gave, so this is sort of like the chi-squared of correlation. I have this data set, which is basically from Wikipedia, of relationship between IQ and how many hours of TV watched. And if you correlate them, so the way you would do this is you'd say correlate data. So this is this data set. And method equals Spearman. And you do that, it'll just compute that. So in this case, no method is going to show it. So it shows that there's not a very strong correlation between IQ and number of hours of TV watched. All right, so what do we discuss today? Correlation is a way of showing some connection between two data sets. It's not a perfect way, but it's a very good way, and it should be one of the first ways you should look at. Correlation does not imply causation. It just implies a hidden factor. It implies that there's some connection, but we don't know if it's causal. It can be confounding factors, as with the ice cream. And as I say, lack of correlation doesn't mean two data sets aren't connected. So let's not confuse cause with correlation. If you want to predict, correlation may be sufficient. If you want to blame, you need to do cause. So don't confuse cause with correlation. Where there's smoke, there's fire. I don't know how to get smoke without fire. I think you can establish there's a pretty good causal connection between smoke and fire. All right, so next week we're going to talk about linear models, and then we'll have the midterm. And after next week, we'll have enough data and enough methods in hand to start doing some real damage and start analyzing some data sets for real. I will put out the reading later this week, and I believe that's it. So before I go, let me wish any fathers out there a happy Father's Day. What will be the format of the midterm? Okay, so that's a great question, and it's certainly worth asking. What are you going to be expected to do? And I haven't written it yet. It's going to be mostly expecting you to do the kind of things. I'm going to give you each data sets, and I'm going to ask you to compute a bunch of information. Now, I had a professor once who said, my tests are open book, and everything on my tests are going to be from the book. And I thought that was a great way to do it. So if you have the lectures in front of you, all I'm going to do is look for things that I expect you to have learned from the lectures, that there's illustrations of how to do it in the notes, and I'm going to ask you to do it. So the only reason I can say I'm exactly sure about the format is mostly it'll be involved using R to compute things. I'm not sure to what extent I'm going to add true-false questions, or there'll be no essays. And the purpose of the midterm is for you to gauge how well, and for us to be able to gauge how well these lectures are going. Does that answer the question? No, it'll be an online, so the question is, will it be during class or an online submission? It'll be an online submission. It will not be during class. We will not be taking a class time. So I'm going to talk with Manish about this and my TA Steve, but my feeling is that I will give it to you sometime next Sunday, your evening, and you'll have a day or two to sort it out yourselves. That's where things stand now. I will talk to Manish, who's returning to the United States today. I'll talk to him a little bit later in the week about exactly what he thinks the best thing, and Steve may have input, and we will get it out, and it'll be given next week. All right? Any other questions? Well, in that case, please clarify format again. So I don't have an exact format. What probably you're going to have, I mean, the go-to training has a format which allows you to submit answers online. I think it's going to do that. So what's going to happen is I will create the test and give you it next Sunday. I don't know if, depending on how long it is, I don't like long midterms. I think, it just should be, the main point of a midterm is for everyone to get some idea of how they're doing relative to what I think is, a decent performance. So the basic format will be, you'll get a data set somehow, and you'll be expected to perform various statistical manipulations on it based on the lectures you've been given so far. Now, we will do linear modeling. So it's conceivable something about linear modeling, regression models will be on there, but it's not going to be anything crazy. It'll be just basic stuff. All right? And how it's going to be returned, I need to discuss with Manish and Steve, because we need to just think about how that should be done. Does that answer the question? All right. All people wish me happy Father's Day. Thank you. And if there's any fathers out there, happy Father's Day to you right back. All right, that's it. I'm going to sign off. Have a good rest of your day.